All right, hey everyone, welcome to week 38 of Chill Kernel Hacking for Fun. Today's stream is pre-recorded because I'm away, and so I pre-recorded this. This is going to be a bit of a shorter stream than usual, but I'm pretty excited. And so, just in terms of the ordering of the stream videos, if you were watched week 36, so it's going to be week 36, and then in terms of content, week 38 is what I'm doing right now, and then watch week 37 because I'm filming this right now. Then I will film week 37 a little bit later, and then this one will be released in 1 week. Sorry, it's like kind of confusing, but anyway, so last time we made a lot of progress, and so I have been debugging a lot of issues lately. And I've been trying to document what I've been seeing, but basically there are kind of two main problems. So for one thing, I have this Kimu crash where after adding the code for lab 4, for some reason, Kimu is crashing for reasons related to setting up multi-core support in the OS. And yeah, that's kind of mysterious. I was able to find out a way to kind of prevent that crash from happening by commenting out a little bit of the multi-core bring up code. But then that leads to this other issue. So the kernel, so Kimu doesn't crash in that case, and the kernel successfully runs this user space program that causes a division by 0. But then there's this problem where the kernel is crashing on processing that exception. So last week in week 36, I debugged this, and I figured out that it's related to the stack somehow. So basically there's this code here that takes this pointer as an argument, and then there is this CR3 page table switch, and then the E variable is used. And what I was observing is that a valid pointer is being passed in, but then here, after the CR3 switch, the E pointer actually becomes a null pointer and crashes later. And the reason it's becoming a null pointer is because the stack memory gets changed somehow. It seems like we're running on some stack before here. We swap a CR3, and then the memory, the virtual addresses that the stack used to be, or the virtual memory addresses of the stack, switch their mapping and then now point to a bunch of zeros in memory. And that causes this thing to become a null pointer when the assembly code, or the code of the function, reads memory again, because that value is not stored in a register for the lifetime of this function. It's queried basically from the stack memory over and over again because we're on x86 32-bit. So that's as far as we got last time. So now the key question is, what's going on with the stack here? And that's what I'm going to try to figure out right now. So as usual, I'm kind of coming in a little bit cold here today, so I need to assess what the state of my working tree is. Okay, so what we're seeing is I am commenting out some of this code. This commenting out makes Kimu not crash anymore. I'll need to maybe handle that later, but for the moment I'm just trying to figure out why. I'm trying to debug this secondary issue, and so I'm just kind of temporarily making Kimu not crash so the code can keep going forward. And I'm simplifying things, and rather than jumping into the scheduler, which is kind of incomplete and I don't understand it well yet, I'm just directly triggering execution of the first user space process, which is this division by 0 program. Here I have the code for debugging this null pointer dereference, and I was just printing out a bunch of stuff and adding some asserts, basically. Yeah. And then lastly, I have this little comment with a possible question about what might be wrong. So basically what I discovered is I believe I have a bug here. The bug is somewhere here. If I comment out this line, we do not have the null pointer dereference, and execution simply works. Like, let me, that's just what we see here. I'm going to take a screenshot of this. There. So when I take the code, I comment out the boot map region in, there's no more null pointer deref, and the code just works correctly. And this is what, actually wait a second, no, this is this is not it. I need to, okay. Okay, yeah, so I need to actually run this one more time to observe it. So I'm going to comment out this key code. I'm going to run it again, and we're going to observe that. Oh, is I also, yeah, I need to do a couple things to make this work. I need to comment that out and also disable this internal unit test. Yeah. Right, and this is how it looks when it is working. What we see here is that we catch the exception, and we're in this kind of function that's printing out all this E pointer, and we can see that it does not become a null pointer, and we successfully run this and then hit this no runnable environments and then drop into the kernel monitor. So that's what it looks like when things are working. And so now the idea is to figure out why, like really what is going on with all this stack stuff here. And I think I can do this. This seems fairly like, yeah, like a tractable bug for me. And I'm going to spend about the next 45 minutes trying to look into it before I take a break and then record week 37, where we'll continue with this. Yeah, I'm just going to grab some water really quick. Okay. So really it's all about the stacks. And I even have this kind of comment, but basically what's going on here is that we are kind of, I guess, migrating to a different stack is kind of the idea here. So before we are adding this, like for the entire history of this kernel, and actually I need to review this because my memory is a little bit shaky on exactly the stack situation, but there's just kind of this like stack that the kernel runs on as soon as it exits the assembly code and jumps into the C code. It's called the boot stack. And I'm just going to take some notes because this is going to be relevant. So where should I take these notes? Okay, I'll just do it down here. So stack situation, make this dark green. So it's the stack situation. So kernel boots up using the boot stack. Kernel eventually migrates to per CPU stacks when we add multi-core support. I'm just kind of writing down what I know about the situation. It's helpful to consult the memory layout. This is kind of what we are seeing. So the kernel eventually migrates to per CPU kernel stacks. And I think it's going to be fairly obvious once we actually debug this. But there's some problem in the process of doing that. I suspect it's fairly obvious. So here's where the boot stack is declared. The boot stack is actually just a region of space allocated in the kernel binary. And it's a K stack size, which is like several kilobytes actually. And so that's the memory that our stack is. It's like this region inside our own data section of the binary, basically, that we use as the stack. Per CPU K stacks. Here is where we declare the other region. So this is where we declare the memory for the per CPU kernel stacks, which which uses a similar strategy. It's literally just a global buffer it's basically a global variable. It's just this big, large buffer region that's inside the kernel binary. And that's going to be used as the backing memory for these stacks. And so we're going to basically map these areas of virtual memory to point to these kernel stacks. And I think there's some kind of like very straightforward, naive problem of that we were like running on this boot stack, and we were running on the boot stack, pushing arguments, and in particular, pushing this E environment pointer onto the stack. And then something along the lines of we just like abruptly and harshly swapped the stacks and redirected the stack memory to be backed by completely different physical memory that's filled with zeros. And so it's pretty obvious that we should expect that to not work if we just so abruptly effectively zero out the stack region, is what that effectively does. So yeah, I definitely did something wrong, I believe, and I think I can figure it out. But this is starting to get a bit messy. So I'm going to commit some of this stuff, actually. I'm going to commit this as a temp. Disable QEMU crash, simplify, and simplify to not use scheduler. Okay. This is relevant for us, and this is just some debug. this is all useful stuff to have around. I think these assertions are good. And I'm just going to commit this as a temp also. Okay, so now we're in a bit more of a clean state, and I'm just going to stage this. Right. So how do we debug this? So I guess first, I think I want to have a bit stronger understanding of the stack situation, because I have this understanding that we have the boot stack and we have these per CPU kernel stacks, but I'm not sure if I'm forgetting something. So I just want to walk through the boot process one more time and really just clarify things. Entry.s. So here we are in entry.s, which is the entry point of the kernel. We do our basic setup. We enable paging. I guess we enter in protected mode already, I believe. So all we need to do is enable paging, basically. Jump into high memory. Let's relocate ourselves. And then jump into C code, which we do by nuking the frame pointer, setting the stack pointer to the boot stack top, which is this thing, and jumping into C code. So let's follow i386 init. No, that's not right. i386 init. Okay, here we do a bunch of kind of boring stuff. We initialize the console. It would be kind of annoying to walk through actually absolutely all of this. Maybe from a high level point of view, we set up virtual memory. We kind of set up our physical memory allocator memory. Yeah, the design of the kernel is kind of confusing. It's the borders between like internal components or abstractions are basically don't exist. Like everything just is totally fluid and intermixed, which is not great design. Okay. Then we're basically mapping memory. Yeah, I'm kind of also forgetting. Like, I don't know if if it's necessary to go into this level of detail, but I'm also trying to recall the virtual memory kind of evolution that happens. So at first, the first thing that happens is there's this ultra basic virtual memory setup that basically only maps the kernel. Kind of like right here. Alright, so this is the very old diagram. So basically, this is physical memory. The kernel is just kind of sitting here, loaded at 1 megabyte. And in terms of like the really basic virtual memory setup, I believe it was actually just this block, this thing is mapped, and this thing is mapped. And so the kernel is running here in high memory and can access these high virtual memory addresses which resolve correctly. And that's all that existed. And then eventually the goal of this meminit thing was to graduate to more of the actual production virtual memory layout, which is implementing this more of this mem layout kind of thing. So we map a bunch of stuff like this environments thing. We map the boot stack. This is important to understand. So this function, I always kind of forget it. You give it a destination virtual address range and a physical address range that you want to be basically like mirrored or mapped. Or a virtual address range that you want to map to a given physical address. And so all we do is we just map the K stack region to the boot stack. Yeah. And so K stack top. Yeah, it's right here. So I am feeling a little bit confused about this boot stack versus this mapping. So we were running using the boot stack before, and we were using virtual addresses to set that up. Because we already enabled paging. So now we're here, and K boot stack top is going to be a virtual address. I think it might be useful to be in a debugger. Be relocated. So step I p boot stack top. It's unknown type. Cast it. Boot stack, that's a very low number. That's a physical address. So so ESP currently is the whatever stack we inherit from the bootloader, I think. We continue to run on its stack, although we're not using the stack. And I just want to, so now if I step I, I'm trying to figure out whether that's what I expected to see. I'm not really sure it is. Wait, what? It's unknown type. Really? Oh, I see. Wait a sec. Is that a dereference? That doesn't look right. I think this is just a normal variable use of this symbol. But also, why is it saying entry to page dir? Maybe I need to print the address. Something is super strange. I'm not understanding this. It looks like our stack is pointed at entry page dir, which is extremely wrong. Entry to page dir is like our page tables. Let me just do one more step in. So now we're in the C code of i386 init. And here's our stack. I'm still a little bit confused, but whatever. So here is so understanding the stack, yeah. So here i386 init, and just to clarify, what or k stack top. Okay, kern base is here. Kernel stack is here. Okay, right. So what we're seeing here is that we are not running in this K stack region, which makes sense, but because we didn't do anything, like, it makes sense because all we did is load the boot stack top symbol into ESP. Maybe that was like very weird what we were seeing there. What I kind of want to do is just do like an nm kernel. Let me be read elf kernel and look for a boot stack top. Here we get something a little bit more sensible. Yeah, this is a bit more sensible. So this explains what we're seeing here. I don't really know what was going on here though. I mean, well, actually, yeah. So it's, yeah. So this makes sense. What just doesn't make sense is why it says entry page dir. Although, so this, it just happens to maybe be a coincidence that they have the same address. No type. Okay, that's a bit weird. There's probably some easy explanation that I don't really understand. Kind of weird that they have the same adder. Page tables. Okay, let's ignore that. So ignoring that weird thing, this totally makes sense. And so what's happening is that we have our memory, you know, we have physical memory over here. I'm just gonna redraw this again. The kernel is here. And it's in low memory, like, and embedded into the kernel is a stack region, and just embedded into the kernel binary. So somewhere in high memory, the kernel gets mapped. I'm just going to call this virtual physical. And actually, maybe I should just copy actually both of these. That goes into high memory at kern base. Immediately below that is k stack, basically. And this region maps here. It's on a straight line. Yeah, I'm gonna move this down here specifically. So this whole thing maps here. And basically we just, the stack pointer is just simply pointed here. And that's how the, and then the stack is used from there. Eventually, we actually want to point the stack here, and that's the thing I actually have no memory of doing. Eventually, after we set up the actual stack, we somehow. Oh wait a sec. No, never. At some point, yeah, we want to probably stop using these virtual addresses for the stack and then start using these. But what happens, so this whole region, can I maybe duplicate this? So this whole region gets mapped. And furthermore, the K stack gets mapped specifically to here. So these kind of alias each other. This stack memory and this K stack memory both point here, I believe. Maybe I'll delete some of these arrows to make that clearer. These kind of alias each other and point to the same place. Okay, so that helps clear a few things up in terms of just where we're running. And then, so eventually, yeah, so eventually we set up, we map a bunch of memory. Yeah, so we make this mapping. We like draw this arrow between this region. So initially we only have basically this arrow. Now we also add this mapping. But the confusing thing I don't quite understand is so far so far this is like unused as far as I really know. However, I remember in our past investigation printing out, because that is actually using the K-stack region. This is printing out. This is like dereferencing a stack address, and that address is below the current base, so it's actually in the K-stack region. So We set up the mapping, it's no longer used. It's not used still, it's not used yet. We map more things. And then here's, yeah, right. So here's where my kind of buggy code is running or something. And okay, that's interesting. I wonder if this is necessary then. Yeah. Then there's this some check, and then we load in the new the page tables. So what I am somehow what I'm looking for, at what point do we transition ESPs to start running here? I think that's the point I don't really understand yet. How would that even work? Is it just... Is it part, like... I'm thinking about the function prologue, maybe? Is there any possibility? But I don't really think so. What's like a env free, for example? That was just what I was looking at last week. It's like a classic example. No, it's hard to find. We never pop. We add something to ESP. What does this do, actually? Yeah, I'm actually kind of not understanding that. I think that's maybe kind of a basic thing. But yeah. But okay, basically, so wait, so before I go too deep into that, so I'm really wondering if this is redundant now, because now we basically just do the same thing. Map per CPU kernel stack starting at case stack top for up to n CPUs. For CPU I, use the physical memory that per CPU case stacks I refers to. As its kernel stack. Okay, but now maybe I'll just go back one more level. Okay, so then I think a lot of the rest of this is not super relevant. Env init just... Okay. This is not super relevant, I think. This is also not. Env init. Check env init. Okay, yeah, then trap init. This is also not super relevant. This might be. This is setting up per CPU exception handling stuff. but actually in this branch, I actually have not implemented exercise 4 yet. So that's probably an issue, but it's only really an issue when we have multi-core running, which we don't yet, because it's like seems to be broken and crashing QEMU. So I think that it's okay to leave it like this. Basically, this is just saying, oh, that might be where it happens. That might be where it happens. In the interrupt handler, we specify this k stack top to run at. So I think what happens is okay, so first we are running in physical memory, and ESP is pointing to, like, I don't know, some bootloader stuff. And then we switch into C code and point it up here, and we run our stack from here. I think we do that for a long time, until an interrupt or exception happens. Initialize the TSS slot of the GDT. Man, it's been a minute since I worked with these really specific details of the GDT and the task state. I know, here's what I know. I know that the task state segment has a lot of other stuff in it for hardware context switching. The majority of it is not used, because, yeah, the majority is not used, except for this bit about stack switching during interrupts, which actually is used. And that's where the CPU knows to reset the stack, basically. And here we set it to k stack top. Are we using k stack top anywhere else I should know about? Defined here. It's in a lot of comments. I'm mapping the kernel stack into the user space processes here. Yeah. And this is all the kernel, again, mostly comments here. This is part of some internal unit tests and stuff. And then this is here, this is like the main place we actually use it. So that helps put the picture together. So my working understanding of this system is like, okay, we initialize to point here, and we run here for a very, very, very long time, I think. I'm not aware that we ever really explicitly switch over here to the, like, proper region that we should be running at. So I think we just run here for a long, long, long time, leaving this totally unused. And then, well, actually, we run a user space process, and that, yeah, sets ESP to like a low memory, and then user space is running. Let's see, where does that happen? It's not totally important, because we run here. Eventually we drop into user space, which resets the stack to very low, and run would be the place. We pop the trap frame to restore, and drop into user mode. And I see. I think that, and the trap frame is constructed even before here. The trap frame is constructed, trap.as, oops, trap.entry. Something like here. Let's see. Where do I find the trap frame? Yeah, so the trap frame, something like this, maybe. So we like, yeah, it's also been a minute. We're like, so in the trap handling, we have all these macros that define these various entry points for the different exceptions, which push some very basic information about them, such as their trap number, and optionally a little bit of padding in case there was no error code. And that kind of crafts this, starting from here, basic. We're kind of, yeah. Push DS, push ES, push all the registers. Load into DS and ES for some reason. Oh, to transition into the kernel, right? For the kernel, yeah. Yep. Because the kernel needs to have its segment selectors set properly. And then we push a pointer to the stack, onto the stack, and then call this function, call the trap function. Yeah, this is like kind of embarrassing that I forgot. All this stuff. But I think this is important. So I think basically the key point though is the CPU pushes a bunch of stuff that I'm like kind of not remembering, but like potentially a lot of stuff. I think I just have it in Neuro somewhere. Over here. Yeah. They did automatically push by CPU. We manually push the trap number, and it kind of looks like this upside down thing. So the CPU pushes all this stuff. Maybe the error code, maybe not. And then, yes, so that's just what we're seeing here. CPU definitely pushes like all of this stuff except for the error code. It might not push that. And so then we either do that or don't do that. And so here we either, for a lot of this case, we push the 0 for the error code, and then we push the trap number, and then all traps takes over from there and pushes the rest of these things like the DS, the ES, and the registers. All that is to say though that the CPU pushes the ESP And yeah. Okay, so wait, but then the question is how, yeah, I'm kind of running out of time because I need to take a quick break before I start actually streaming for real today. It's env run. That's kind of like this whole thing. Wait a sec, what? Env create. So something about here in env create. Yeah, env alloc. Here we go. Yeah, we set up the trap frame and we point to U stack top, right? So that's also just a key moment as far as the story of like the stack goes. So it's basically just like 1, start running on boot stack. 2, do that for a long time. 3, enter user space, switch to user space stack via trap frame U stack top. 4, interrupt exception happens, switch to K stack top via TSS and IDT. Okay, nice. That is much better understanding of like the lifetime of the stack. I'm gonna stop the stream here, take a quick break, and then record week 37. So that's it for today. Thanks a lot for watching, and I'll catch you next time. Peace.